Chapter 14 Newton's Method. In the previous video, we discussed the gradient descent method as an optimization technique for logistic regression. In this video, you will learn about another popular optimization method, the Newton's method. The gradient descent method and the Newton's method are both used to find optimal values of parameters, but there is a major difference in their approaches. The gradient descent method calculates the gradient of the loss function and gradually updates the parameters in the opposite direction of that gradient. This process is iterative and continues until the value of the loss function is minimized or sufficiently small. The gradient descent method is simple and easy to implement, but it can be slow to converge and is sensitive to the choice of learning rate. While the gradient descent method uses only the gradient computed by the first-order derivatives of the loss function, the Newton's method also uses the second-order derivatives. By using second-order derivatives, the Newton's method has the potential to converge more quickly to the optimal solution by also taking into account the curvature of the loss function. The Newton's method uses a Hess matrix that includes information on the second-order derivatives. Specifically, the amount of parameter updates at each iteration is calculated using the gradient and inverse of the Hess matrix. This allows greater progress to be achieved with each step-by-step update, which in theory is expected to converge faster than the gradient descent method. However, the need to compute the inverse of the Hess matrix increases the computational costs, which can be disadvantageous, especially when the number of parameters is large. The Hess matrix for a function is a matrix whose elements are the second-order partial derivatives with respect to each variable. For an n-variable function, the Hess matrix is defined as a square matrix with n by n. Let's use this function as an example to create a 2 by 2 Hess matrix. The first-order derivatives of this function look like this, and the second-order derivatives look like this. Thus, the Hess matrix is expressed like this. A matrix A is said to be positive definite if this inequality holds for any non-zero vector x, where xt denotes the transpose of x. If the Hess matrix derived by a function is positive for any non-zero vector, that is, if the Hess matrix is positive definite, then this function is locally convex at the point this vector represents. So, this function may have a minimum value. Thus, using the positive definiteness of the Hess matrix to represent the curvature of a multivariate function is an extension of the property that second-order derivatives represent the curvature of a univariate function to multiple dimensions. Let's look at the steps of the Newton's method. Although the method used is different, the procedure is basically the same as for the gradient descent method. The Newton's method also aims to maximize the log likelihood through these steps. Before computing the gradient, we need to set parameters' initial values. If the parameters are beta 0 and beta 1, then we need to set the appropriate initial values for these beta 0 and beta 1. These initial values will be set to 0 or some other random value. The next step is to compute the gradient and Hess matrix. We compute the gradient of the log likelihood function using the values of the initial parameters. That is, we calculate the value of the first-order derivative of the log likelihood function. This gradient indicates how changing the parameters will increase the log likelihood. Besides, we create a Hess matrix by computing second-order derivatives of the log likelihood function. The Hess matrix represents the curvature between parameters and helps to adjust parameter updates. Next, the parameters are updated using this equation. Here, beta old is the parameter before updating. Beta new is the updated parameters. H-1 is the inverse matrix of the Hess matrix. And nabla L beta is the gradient. In the fourth step, determine convergence, the convergence is determined based on the same criteria as for the gradient descent method. So, why should we use inverse Hessian matrix instead of the Hessian matrix itself? It is because the inverse Hessian matrix is the matrix that satisfies this equation, where I is the identity matrix. This means that the inverse Hessian matrix is a matrix that cancels out the effect of Hessian matrix when multiplied together. Therefore, by multiplying the inverse Hessian matrix with a gradient vector, we are essentially removing the curvature information from the gradient vector and obtaining a vector that points to the direction of the maximum change in the log likelihood function. This direction is closer to the true optimum than the direction of the gradient vector, which may be affected by the curvature of the function. If we were to use the Hessian matrix instead of the inverse Hessian matrix, we would be multiplying the gradient vector with a matrix that amplifies the curvature information, and we would obtain a vector that points to the direction of the minimum change in the log likelihood function. This direction is farther away from the true optimum than the direction of the gradient vector, and it would lead to lower convergence or even divergence of the algorithm. We should know that the inverse matrix of the Hessian matrix does not remove the curvature information of the Hessian matrix itself, but it removes the curvature information from the gradient vector. The gradient vector is the vector that points to the direction of the steepest ascent of the log likelihood function, but it may be affected by the curvature of the function. By multiplying the inverse Hessian matrix with the gradient vector, we essentially apply the inverse transformation of the Hessian matrix to the gradient vector, and we obtain a vector that points to the direction of the maximum change in the log likelihood function. This direction is closer to the true optimum than the direction of the gradient vector, and it leads to faster convergence of the algorithm. The reasons why the Newton's method converges faster than the gradient descent method are the following. The first is the use of curvature information. The gradient descent method uses only the gradient of the function to determine the direction of the next step. This method advances in the direction indicated by the gradient with a constant step size, but does not take into account the curvature or shape of the function. As a result, the path toward the optimal point may not be straight and may be inefficient. The Newton's method uses information from the Hess matrix as well as the gradient of the function. The Hess matrix indicates the local curvature of the function, which allows the direction of travel and the step size at each step to be adjusted according to the curvature. The use of this curvature information allows for a more direct and efficient convergence to the optimal solution. The second is efficient step size adjustment. In the Newton's method, the parameter update steps are calculated using the inverse of the Hess matrix. This inverse matrix allows dynamic adjustment of the step size based on the shape of the function, optimizing the way it advances at each step. For example, where the curvature of the function is steep, one can advance carefully in small steps. When the curvature is gentle, one can advance quickly in large steps. However, there are conditions for efficient convergence of Newton's method. The Hesse matrix must be positive definite and computable. Also, the computational cost of computing the inverse of the Hesse matrix can be high, and a gradient descent method or a variant of it may be preferred, especially for large problems with a large number of variables. Let's summarize the points. Newton's method for logistic regression is an iterative algorithm that updates the coefficients of the model by finding the direction that maximizes the log likelihood function. The Hessian matrix is the matrix of second-order partial derivatives of the log likelihood function, and it measures the curvature of the function at a given point. The inverse of the Hessian matrix is used to scale the gradient vector, which is the vector of the first-order partial derivatives of the log likelihood function, and it points to the direction of steepest ascent. By multiplying the inverse Hessian matrix with the gradient vector, we obtain the Newton step, which is a more accurate approximation of the optimal direction than the gradient vector alone. The Newton step is then added to the current coefficient to obtain the updated coefficients for the next iteration. This process is repeated until convergence is achieved, or a maximum number of iterations is reached.